In 1940, the concrete and steel deck of the Tacoma Narrows Bridge was caught violently twisting in the wind before tearing itself apart. For over 80 years, physics textbooks have pointed to this disaster as the ultimate example of resonance. They compare it to a singer hitting the exact right pitch to shatter a wine glass. But that textbook explanation is a myth. The bridge was not destroyed by resonance. So what actually brought down thousands of tons of steel? And what does physical resonance actually require? Labeling this collapse as resonance is a lazy shortcut. It completely ignores the strict mathematical precision a physical system actually needs in order to absorb and amplify energy. To see how a structure absorbs energy, we look at a linear time-independent system. It has three basic parts: a mass, a spring, and a dashpot to simulate friction. This differential equation describes that exact setup. The left side balances the mass, the friction, and the stiffness of the spring. The right side is the external force pushing against it. If you push this block once, it wants to bounce at a very specific rate. We call that specific rate its natural frequency. Because of friction, that bouncing will eventually fade out to zero, unless an external force keeps pushing on it. This equation defines the predictable motion of almost any linear mechanical structure responding to an external load. For true resonance to occur, that external push has to follow a strict first rule. It must be a constantly oscillating, sinusoidal wave. Think of a tuning fork. When struck, those metal prongs vibrate at a steady, continuous frequency. This graph shows what happens mathematically when the frequency of that external oscillating force perfectly matches the system's own natural frequency. Usually, we calculate the system's movement using the standard exponential response formula. But when those two frequencies align, the denominator of the fraction hits zero. The math breaks. This exact mathematical failure state is true resonance. We have to bring in a completely new equation, the resonance exponential response formula. Notice the new variable t in the numerator. That t stands for time. It dictates that as time passes, the amplitude of the system's response will keep growing larger and larger in a linear upward trajectory. True resonance is a state of unchecked mathematical growth, triggered exclusively by a perfectly matched oscillating force. Let's bring those mathematical rules back to the events at the Tacoma Narrows Bridge. The external driving force pushing on the physical structure that day was the wind howling through the gorge. The issue here is the input signal. While wind is turbulent, it lacks the rhythmic back-and-forth oscillation of a sinusoidal wave. It is a steady flow of air, not a vibrating hum. Because the wind did not oscillate, it was mathematically impossible for it to trigger the time-based amplitude growth required for true resonance. The actual scientific cause of the bridge's destruction is a phenomenon known as aeroelastic flutter. Flutter is highly complex and nonlinear. As the bridge twisted, the solid deck caught the wind at different angles, which actively fed energy back into the structure. The bridge powered its own destruction. If engineers misdiagnose a failure like this as simple resonance, they might try to fix the bridge by just tweaking its weight. That completely ignores the fatal aerodynamic flaw. Applying the strict definitions of these equations forces engineers to look past the obvious and account for the actual dynamics at play.